All right, so I've set up, oh, you can't see that. There we go. All right, so I've set up both examples where we're dealing with hypothetically the 20 sales calls and the 2,000 sales calls, because I want you to see how big of a difference it makes when you're comparing a small expectation to a large expectation. All right, so what I have here is our two salespeople, Sal and Sue. And I've already filled in these first two columns because reasonably, this would be the information you would start with, right? My E is my expected value, okay? I'm expecting an even 10 and 10 split. We'll do the top example first and the bottom. We'll just keep things cleaner. And O is my observed numbers. Remember, your observed numbers are your actual numbers, okay? So I had my person in the company go through the actual records and see that my observed numbers, my actual numbers, is that they were split 18 and 2. So step one, and I have already worked out the math for this. If I look at my cheat sheet, don't judge. Okay. So step one is we add a calculation for observed minus expected. O minus E. So we're going to do O minus E. Can you see him or am I in the way? I'm kind of in the way. Okay. O minus E. So we're going to do 10 minus, or long day. We're going to do 18 minus 10, which is 8. And we're going to do 2 minus 10, which is negative 8. Observed minus expectation, O minus E, or observed minus expected. Now, right away, and here's why I said it doesn't actually matter which order you subtract them in. Right away, you're going to see an issue. Because if we're only dealing with two possible categories, and even as we get bigger, if we're dealing, no matter how many categories we're dealing with, these are always just going to cancel each other out, right? That's always going to end up back at 0 if we try to add them together. So what we're going to do is to get rid of that effect of just canceling them out, we're going to square them. So our next column here is going to be O minus E squared. What's 8 squared? 8 times 8, 64. What's negative 8 squared? Negative 8 times negative 8. Anytime you multiply two negatives, you get rid of the sign, so you still have positive 64, okay? So that's our next step. So we square O minus E to get rid of the negatives. So with chi-square, our chi-square table for significance is always going to be a one-way table because we're not going to have negative numbers because we're squaring them, okay? So our next step is where the number of how many expectancies we were dealing with becomes significant, because now what we're going to do is we're going to divide this by the number that was expected. So now we're going to have O minus E squared all divided by E, the number that was expected. So in this case, we're going to have 64 divided by 10, which is 6.4. Again, we're going to have 64 divided by 10, which is 6.4. And our last step, what we're going to do for our chi-square, get rid of this line, is we are going to add these up. So we're doing this plus this, okay? So we're going to take the sum of these, which remember, your textbook does sum as this, which is the capital letter sigma, okay? And so this is 12.8, right? So this sum is equal to 12.8. And that number is your chi-square. That's all there is to it. So let's look at how that makes a difference down here with these numbers. I don't know where that blue was that I used. Okay, so again, our observed minus our expected, O minus E, 1,008 minus 1,000. This is still 8. 992 minus 1,000. This is still negative 8. So when we square these, this is still going to be 64. This is still going to be 64. I'm not actually getting to the difference until this step where I'm dividing by what I expected, right? Because now, instead of 6.4, this becomes 0.064 when I divide 64 by 1,000. 0.064. So now, when I add these together, instead of 12.8, I have, remember I add, so now my sum is 0.128 for my chi-square. And so now we look at our significance table. Now, I'm trying to stay out of the way of this in case you're trying to write stuff down. If you look in the back of your book at your chi-square table, one thing you'll see is that there's one more step here. Because in order to evaluate how significant it is, you have to know your degrees of freedom. For a basic chi-square, your degree of freedom is going to be the number of categories, number of possible outcomes, minus 1. So let me find a place to write this where I'm not sideways. So DF equals number of categories minus 1. So in this case, it'd be 2 minus 1. So it would be 1. So our DF, degrees of freedom, equals 1. So now we can look at our chi-square table and see if does a 12.8 meet the cutoff for significance for a chi-square test with only 1 degree of freedom. So if you actually look at that chart, I'm out of room to write any more numbers on this board. If you look at that chart, what you will see is that for a 0.05 level, our cutoff would have been 3.841. So if our cutoff is for 0.05 significance and it needs to be higher than 3.841, does this split of 18 clients versus 2 clients meet that? Yes, it gives us a chi-square of 12.8. 12.8 is much higher than 3.841. And just for curiosity, our 0.01 level would have been 6.635. So it would have been statistically significantly different, even if we were evaluating at the 0.01 level. So what this tells us, again, remember how we use this language. What we are saying is that statistically, we have results that there is less than a 1% chance that this is due to chance or coincidence, or this is just how it happened. Okay? So in this situation, we would reject our null hypothesis. Because remember, the null hypothesis was saying there's not going to be a significant difference between these groups beyond what can be accounted for by chance. That's not true. We reject our null hypothesis. But now let's come down here and evaluate this situation where it's 2,000 clients split up with an 8-client difference. In this situation, we saw that our chi-square was 0.128. Now in this situation, 0.128 is most definitely not larger than 3.841. We're not even close. We're not even on the borderline here, all right? So this is not statistically significant. There is a really, really solid chance that these 8 count differences are based on chance, right? Sue took an extra week of vacation. Sue was gone sick a couple of days. Sue got up to go to the bathroom more than Sal, so Sue wasn't at her desk as often to answer the phone calls, whatever it might be. But it's a coincidence. There's no favoritism or something happening in this situation. There's not a statistically significant difference. So in this example, we could not reject our null hypothesis. There is not a statistically significant difference between the observed and the expected. Now, all right, I think that's everything in my notes for this. Now, I'm going to reset this board, and we're going to make this a little more complicated. Because what if you have two levels going on? What if, to use this example, I'm not just interested in the distribution of clients. Let me use a very misogynistic and not okay example that unfortunately still happens a lot in sales because I have lots of friends in sales and I know this. Let's say that the complaint isn't that I don't think I'm getting as many clients as them. Let's say the complaint is Sue is saying, I feel like all the male clients are given to me. I am a young female and I feel like all the male clients are given to me because they think that since I'm pretty and young, I would be able to sell more things to male clients. So I'm always getting male clients. Again, unfortunately, this happens in sales still. But so let's say I don't just want to analyze the number of clients going to each person. Let's say I want to break that down and compare the number of male to female clients going to each person. So now I need to add another layer to my grid. And we can still do this with a chi-square. And what this is going to be called is a chi-square of independent means. So I'm going to stop this video. I will reset the board yet again. I will explain the theory behind a chi-square analysis of independent means. And we'll work through a quick example on that one.